Hello everyone. Let's uh, let's start now with principal component analysis, okay, or PCA. And with PCA, we will be able to reduce the amount of columns or features or variables that we have in our data set, okay? Therefore, reducing the amount of data that our algorithms will have to process while maintaining the maximum amount of information possible, okay? This means that we will have a win-win situation in which, or almost a win-win situation, where our algorithm will train faster and it will be cheaper to store and to process this data, but without losing the actual signal, the actual information with which we want to train and with which we want to create predictions. Okay, so let's start right away with dimensionality reduction and PCA. And um, first of all, as I mentioned, what we want to do is to reduce the dimension of the data, creating a smaller data set, but maintaining all the interesting data, all the interesting information or the signal, okay, without losing, trying to just lose noise while keeping the signal, okay? This is called dimensionality reduction, and this is something we can use in the feature engineering phase, okay, of the machine learning pipeline when we are doing feature selection, okay? We can always take our original features, use principal component analysis to convert those to a new set of features, and then we can select those that contain most of the data. Okay, we will see how can we decide which of the features to keep. Okay, so this, as I mentioned, it's a technique for reducing the data. Okay, it's not an algorithm. It's not like one of the machine learning algorithms which will produce a prediction. Okay, PCA will take a certain amount of features and will return the same amount of features. Okay, which different characteristics, but the size of the data will be the same. Okay, the size of the features will be the same. And the good thing is it allows us to choose a certain threshold with which we can say, okay, these many features I don't want, we can remove them. Okay. So the way it works is it will PCA will create a certain amount of features, as I mentioned, where the first new feature is a combination of all the older features, okay? And this first new feature, this first new principal component, will contain most of the variability of the possible combinations that we created. The second one will be the second one containing the most variability, and so on, okay? So the way PCA works is it takes into account the correlation between variables. Okay. Therefore, if we use only variables that are not correlated, PCA will not work. So my piece of advice here is to check the correlation between your variables, because if all your variables are uncorrelated, okay, it will not work. Okay. There is no point in using PCA, because PCA returns variables that are uncorrelated. So if we are using uncorrelated variables to obtain uncorrelated variables, we're just doing an idiot's job here, because what we want to get is what we already have. Okay, and as I mentioned, this is not an algorithm; it's a technique. It's a piece of the preparatory phase of the feature engineering phase that will allow us to convert our data set. Okay, so let's dig a bit deeper into what PCA needs and what it creates. Okay, so let's say we have our original data set with all my training features here, and the target I want to predict, or the target I want to use to classify my data. Okay, then I will use this feature, this set of features here. I will pass it to my PCA black box. Okay, we'll see what's inside this black box. Okay, and then we will receive a new set of features in which The first one will contain the most variability of all the combinations from this data set here. The second one will be principal component 2 with the second highest amount of variability, and so on. Okay, but in the end, the number of features here in my original data will be the same number of principal components that I will get. Therefore, if I am using a data set with 100 features, okay, I will receive 100 principal components, where the first one will contain the most variability of all the linear combinations from the previous, from the original features, the X data set, and it will, this variability will reduce as we advance through the principal components, okay? There is one caveat here, which is principal component analysis. It's super sensitive to different scales, okay, and skewed distributions, okay. So why is that? It's because the PCA focuses on identifying the data structure based on measurements, based on something similar to distances. And as you remember from all the other techniques and algorithms that we have used that calculate distances, when we have different scales, the calculation of distance will be let's say flawed, okay? Because the higher scales will drag the distance towards their scale, okay? Therefore, minimizing the addition of the smaller scales to the total, okay? So keep in mind that when working with PCA, if we want to work with PCA, we need to have more or less symmetrical distributions and similar scales. Okay, so that's the caveat of using PCA. On the other hand, once we deal with this different scaling and the symmetrical features, okay, or the non-symmetrical features, what we can get is new components. Okay, you can see here that in the slides in the left hand side, the effect of not scaling the features versus scaling the features before PCA. Okay, so you can see in the left hand side of the slide that all the classes are quite mixed up in this region of the two principal components. Okay, you can see in the x-axis the first principal component, and in the y-axis the second principal component. Okay, and on the right-hand side, the same thing, first and second principal components after scaling. Okay, you can see on both y-axis and x-axis that once you scale, the scales are similar. Okay, now we can see that for both x and y, the ranges are from -4 to 4. Okay, which give us a good a good opportunity to classify this data according to these new features. Okay. So this is the main advantage of PCA. So there is one piece of information from our introduction to statistics that we are going to be using a lot when working with PCA, which is the concept of covariance. Okay, the covariance is the measures the how two variables, how two features change together. Okay, and it's calculated as follows in the formula here. Okay, it's nothing but the variance formula, but instead of a variance with itself, it's two different variances. Okay. The result of this formula can be positive or negative. If the result is positive, that means that the variable y in this case increases as x increases. This could be, for example, I don't know, for example, the correlation between temperature and pressure. As we increase temperature in a system, its pressure tends to increase as well if the system is enclosed. Okay. On the other hand, this covariance can be negative. Okay, that means that y decreases as x increases. Using a similar example with pressure. Okay, as we increase the pressure of a system, the volume tends to reduce. Okay, so we can say that pressure has negative covariance versus the covariance between pressure and volume is negative. Okay. From this concept of covariance, we can derive the correlation concept, okay, which is the covariance divided by the product of the two standard deviations, okay. And this, as we are dividing by this by the standard deviations, this will range in between -1 and 1. 1 being perfectly correlated, -1 being inversely correlated, okay, and 0 meaning there is no correlation between the two features or the two variables, as we already know. Okay, so let's continue and let's dig a bit deeper into this covariance. Okay, as I mentioned, we can calculate covariance as follows. Okay, so covariance between these two variables, x and y, is defined as the summatory of the product of each of the components of my first variable, okay, minus the mean times the differences of each component of my second variable minus its mean, okay, and divided by n minus 1, okay. So we can calculate covariance this way. What if we have a data set like this, okay, in which we have 1, 2, 3, 4, 5 features, okay? Then we can calculate the covariance of the first one with the second one, first one with the third one, first one with the fourth one, first one with the fifth one, okay, and so on. And we can keep doing that for each pair of features, okay? If we keep doing this and put it in a matricial way, okay, we can come up with the covariance matrix. Okay, this covariance matrix, is defined as capital sigma, okay, and it contains as the first element in the first row the covariance of my first feature with itself. For a second element in the first row, the covariance of my first feature and the second one, okay? And this matrix is symmetric, meaning that, one second, meaning that all the elements besides, on both sides of the principal diagonal, of the main diagonal, are equal, but on different sides. So in here, this element is equal to this element here, because the covariance of y and x is the same as the covariance of x and y. Okay, that's why this matrix is symmetric. Okay, okay. Now we have a matrix with as many rows and as many columns as features we have. Okay, so if we originally had, let's say, an amount of features of 100 features, okay, in my X data set, okay, with this, my sigma matrix will be a square matrix of 100 by 100 elements, okay. This is how we have defined it, and this is how we will use it, okay. So, okay, now we have a square matrix that contains a bunch of numbers, okay, because in the end, each one of these elements represents a number, okay. So what can we do with these numbers, okay? Well, there is something in algebra called the spectral decomposition theorem that says that for any symmetric square matrix, okay, there exists another orthogonal matrix U such that this happens, okay? What's this that happened? Okay, let's go step by step. Let's first define our sigma matrix, which is my covariance matrix, okay? This is what we just did up here, okay? And it's a square matrix which is symmetric. Now, this spectral decomposition theorem states is that there exists a matrix called U such that the inverse of U times my square matrix times U results in a matrix, the lambda matrix here, the green one, which has the following structure. It contains only elements in the main diagonal, okay? And these elements are numbers, okay? So what we have here is my lambda matrix, which is again symmetrical and square, okay? And contains zeros on both sides of the main diagonal, okay? Then we have our matrix U, okay? My matrix U is defined as U11, U12, U1n, U21, U22, all the way until UNN, okay? Where the columns of this matrix, okay, are called eigenvectors, okay? On the lambda matrix, these elements, the elements of the main diagonal, are called the eigenvalues. So now we have converted our original sigma, capital sigma matrix called the covariance matrix, okay? We have moved from this into two new matrices, lambda and U, where lambda is represents the eigenvalues and U represents the matrix of eigenvectors. Okay, this is just some a piece of algebra that we will need for the upcoming steps. Okay, so remember just one more time: if we have a square matrix sigma, in this case, there exists always another orthogonal matrix U, okay, such that the inverse of U times sigma times U equals a diagonal matrix with all zeros on both sides of my main diagonal, okay? Just as a reminder. I keep saying that the matrix U is orthogonal, okay? And this means that for each one of the columns in my matrix, okay? Remember that we have 111, U11 till UN1, U12, UN2, okay? If we check all these vectors here, okay, all the vectors in my matrix, and we are able to represent them graphically, we can see that these vectors are perpendicular in between them, okay? So if we call this vector U1, U2, UN, okay, okay, we can see that these vectors are perpendicular, meaning that the angle between them is 90 degrees, okay? Also, since you already know what projection is when we were dealing with SVM, okay, we know that the projection of two perpendicular vectors, okay, is zero, okay? The projection of U1 onto vector U2 is zero because remember that the projection can be assimilated as the shade it projects, okay? Then the shade U2 projects onto U2, sorry, U1 onto U2 is zero, okay? There is no projection. So this is another characteristic of this U matrix. So recap, we have originally this matrix filled with numbers, okay? And by using the spectral decomposition theorem, we can also get another matrix, another new matrix filled with orthogonal vectors, okay? And another matrix with a main diagonal filled with numbers and zeros on the other sides, okay? So what does all this have to do with PCA? Okay? Okay, perfect. As, um, as I mentioned, the purpose of PCA is converting from my original dataset X, okay, where we have X1, X2, Xn features, into a new set of features or components. We will get a new set of features or components or variables that are orthogonal, okay, and uncorrelated between them. This means that, let's say, for example, for three features, okay, if we have three original features, x1, x2, and x3, okay, we can see that the angle in between them is not 90 degrees. It's not my features are not originally orthogonal. They are not. They have some correlation in between them. Okay. What if we can convert this into something that has orthogonal components? Okay. And orthogonality means they are uncorrelated, okay? Meaning that we have pure features in a way. Each feature will only contain information about it, okay? There will not be a mix of information in several components that such as we could find here, okay? We could say there's always a combination of coefficients or parameters such that, for example, x3 is equal to alpha times x1 plus beta times x2. Okay, we cannot say that with these components here, okay, because they are uncorrelated, they are orthogonal. Okay, you cannot use PC2 and PC3 to create PC1 because they are uncorrelated, they are orthogonal. Okay, so going back to my two new matrices, the orthogonal matrix U and the eigenvector eigenvalue matrix lambda, okay, we can convert my matrix of covariances, okay, remember capital sigma, into a diagonal matrix lambda, which was the eigenvalues matrix, which contains the eigenvalues in the main diagonal and zeros in any other position, okay? This is super, super important because when doing matrix operations using algebra and doing it on a computer, every time we are multiplying matrices, okay, if we have matrices in this way, okay, in this way here, remember our covariance matrix, it's full of numbers, okay? On the other hand, if we can convert the same information into something that only has data in the main diagonal, the computational, let's say, expensiveness of it is reduced a lot, a lot. Okay, what we have achieved is we can do everything faster while maintaining the same information. Okay, so this is a huge achievement that PCA allows us to do. Okay. So now, after having done this, okay, we will have created a new coordinate system, a new variable system. We were moving from x1, x2, x3 into u1, u2, u3, okay? And with this new set of features, with this new coordinate system, okay, we can describe the data better than we could do it in the original coordinate system because remember, these features were correlated. Okay, therefore, there's always a mix of information in between the features, and we cannot have a pure definition for each one of the original vectors in my system of coordinates. On the other hand, with this system, okay, we can do it. Okay, it's way better and it's easier to describe the data in such a coordinate system. Okay, so let's move on a little bit. And let's see it with an example, okay? So far we have only seen letters and formulas, but let's use an example, okay? Let's say my original features, okay, are x and y, okay? This is my data set, over here. And if we plot the data, we see that x and y has this shape, okay? Okay, perfect. This is a typical example of something that could be fit with a linear regression, okay? But we can see that if we project the whole range of my data onto the two features, okay, we can see that for x we have this much variance, and for y we have this much variance, okay? Well, the idea for PCA, as I mentioned, is to create a new system of components, a new system of features, of variables that are orthogonal, okay, such that the first one maximizes the variance of the data when projecting the data onto this new feature, okay? The second one will be the second that maximizes the variance. The third one will be the third one when maximizing the variance, and so on, okay? So if we compare this situation that we have here, let me first make a copy of this so we can compare apples with apples. Okay, copy and paste here. Okay, now we have in my original data the projection of my data, or the variance in the first feature x is this much. Okay, the projection of my data onto the second feature y is this much, okay? And we can see that they are more or less the same, okay? The two projections are more or less the same. But what if we find a new set of coordinates, a new set of features that have the first one maximize the variance alongside its direction, and the second one is the second one, the third one is the third one, maximizing variance, and so on. Now we can see that my projection, or the total variance of my data across this principal component one, okay, is bigger than my original first component, which was x. We can see that by comparing this this variance with this one here. Okay, we have increased the total variance projected onto that new feature. Okay, and the second one, which is principal component 2, okay, will be the second one that contains the maximum variance explained or projected across that axis. Okay, why is this important? Why is this better than what we had originally? Okay, well, if we plot the two distributions of my data across each one of the systems, okay, we can see that when dealing with x and y, okay, the distribution of my data for x and for y, it's pretty similar, okay? It's pretty similar. But if we move from x and y to my principal components, okay, we can see that for my principal component 1, the variance is maximized, okay? And for the second principal component, we have a very different variance, okay? Now we can clearly say that the sum of the variables in order of principal component explain better the data, okay? Explaining the data, or including more information about the data, means having a bigger variance in that feature, okay? That's why the first principal component here, with a greater variance than principal component number 2, contains more information about the data, okay? And as we increase the number of, or as we create new principal components, we will keep explaining the data with less features needed. Okay, that's a beauty and that's the strength of principal component. So let's relate all this we have done with the two new system of coordinates, okay? Sorry, with the new system of coordinates versus the old system of coordinates, okay? Let's relate that with the eigenvalues and eigenvectors that we have defined with our lambda matrix and our U matrix, okay? So, as a recap, remember that the eigenvalues are each individual element in the main diagonal in the from the lambda matrix, okay? And my eigenvectors are the columns of my U matrix, okay? Coming from the spectral decomposition theorem, okay? So with these two matrices, we can create this new system of coordinates that we were talking about, because the eigenvectors will create, let's say, the directions, the orthogonal directions on which my features, my components will lay on, okay? And my eigenvalues will define how much of the projection lies on each one of the directions. Okay, so we could say that for lambda 1 defines this much variance across this direction, lambda 2 this much, okay, and lambda 3 this much. Okay, if we had three features originally. Okay, so now again we have moved from x1, x2, x3, and using principal component analysis, we will have created three new features, which are perpendicular between them, called PC1, PC2, and PC3, okay, which are linear combinations or of my original features, okay. This relation between the principal components and the original features is nothing but, for PC1 we have alpha 1 times x1 plus alpha 2, alpha 1 1, sorry, alpha 1 1 times x1 plus alpha 1 2 times x2 plus alpha 1 3 times x3. Principal component number 2 is equal to alpha 2 1 times x1 plus alpha 2 2 times x2 plus alpha 2 3 times x3. And principal component number 3 will be alpha 3 1 x1 plus alpha 3 2 x2 plus alpha 3 3 x3. Okay, this is the relation between my new coordinates, my new set of coordinates, my new features, my new principal components, and the old ones, which are x1, x2, and x3. Okay, this is what we get when we perform principal component analysis. A new set of features that are orthogonal, okay, that maximize the variance as we move from the first one, okay, principal component number 1, to the latest ones, okay. So this is what we do. Again, the useful of this, okay, is that what we are trying to do is to find information that is redundant. That is, we want to get rid of information that is contained across several of the original features, okay? If we move from the original features to the principal components, we can be sure, okay, that the first principal component will contain a certain amount of information that is not contained on the rest of the principal components, okay? What we can achieve with this is we can say, okay, if my principal component number 1 explains 60% of the information, my second principal component explains 20% of the information, and my third principal component explains I don't know, 10% of the information, okay, with 3 features, we can explain 90% of the original information that we might have had in, let's say, 5 or 10 features, okay? Therefore, we will be reducing the amount of features, the amount of columns in my dataset, while maintaining the information and while maintaining the signal that we can use for predicting stuff, predicting prices, or classifying whatever it is that we need to do, okay? So going back to my principal components and to my the relation between principal components and eigenvalues, okay, if you remember from here, okay, we know that those new variables that have the smallest eigenvalues, okay, remember that this lambda 1, lambda 2, all the way up to lambda n represent how big or small is the new principal component. Okay, so the principal component number 1 will receive the biggest lambda value. Okay, the biggest eigenvalue. The second one will receive the second one, the third one, and so on. Okay, so at some point, okay, we can start comparing the new features, comparing the new principal components, and we can say, okay, if principal component number 50 is so small that the upside of including it is not enough to compensate the extra computation cost of including another feature, then we can remove it because we can be quite sure that the extra performance we get from not using that much computation power will compensate the information that we are losing in such an insignificant feature. Okay, that's why we can use principal component analysis to remove features, to perform feature selection in the feature engineering phase. Okay, so how can we decide how many principal components we want to keep in our dataset? Okay, so let's go. Let's plot this same chart, okay, that we have in the slides, but let's explain it step by step. Okay. So let's say we have, in this case, there is 13 features, okay? We have our original data set containing 13 features, okay? If we use principal component analysis, we will get 13 principal components, okay? These 13 principal components don't contain the same amount of information, each one. As you already know, the first one will contain way more information than the second one. The second one will contain way more information than the third one, and so on, where each previous principal component explains more information than the next one. Okay? So what we can do is we can plot how much variance, okay, is contained in each one of my principal components. Okay, so we can check for each one of my principal components, principal component number 1, number 2, number 3, and so on until 13. Okay, we can check, we can calculate the variance of each one of them. Okay, we can see that for this first one we have beyond 4, 3, 2, and 1. Okay, we can see that for my first principal component, we are here. For the second one, we have dropped in between 2 and 3. Okay. For the third one, we are around 1. Okay. And then it starts dropping dramatically until the 13th one. Okay. We can see that the chart looks like this. Okay. So one of my, sorry, let me uh, name this axis, which is the variance. Okay, we can always define a certain threshold. For example, in this case, we can say, okay, I'm going to keep as many features as they have, as long as they have variance above 1. Okay, so that would mean that if we go with this threshold, okay, we might keep only 3 components. Okay, well, actually in the slides it's 4, but you get the idea. We can decide a certain threshold based on the of the amount of variance that each principal component owns or contains. Okay, there is another criteria. Okay, which is how much cumulative variance each one of the principal components that I keep adds to the total. Okay, with this criteria, what we are doing is adding up the variance as we add up new principal components. Okay, with this axis representing the number of principal components, and this axis representing the percentage of cumulative variance. Okay, so all the variance is represented by 100% or 1 if we are doing it by 1. Okay, so if we start plotting how much cumulative variance is included as we include more principal components, okay, we can see that this chart looks like this, okay, and we can again find an arbitrary threshold that we will have to test extensively using cross-validation, okay, and we can say, okay, I don't want, I just want to keep, let's say, 90% of my explained variance, okay, or the total information, okay. Remember that the cumulative proportion of variance represents the percent of total information contained in the data, okay. So if we choose this threshold, okay, we can say that with 90% of variance, we can keep only 4 principal components and remove the rest, okay. We remove the rest of the principal components because 4 principal components contain 90% of the data, whereas what we had originally 14, 13, 9 principal components contain 10% of the data. Okay, this is the trade-off that we have. How much information we want to lose in order to reduce the size of the data set. Okay. There is a third, there is yet another criteria, okay, which is let's keep only those principal components which have, for example, in this case, variance higher than 1, okay? Well, in this case, if we are plotting the variance of each one of the principal components, okay, then we can see that the first component has a variance of above 4, second component has a variance of around 2.5, okay. Third component has a variance around 1.5, okay. But fourth component is slightly below 1, okay. So this is another criteria we can choose, which is, okay, I just want to keep the principal components which have a variance greater than 1, okay. Then again, there is always a trade-off. How much information are you willing to lose in order to reduce the size of your data? Okay, that's the trade-off that we will have here. So um, as we already know, we cannot plot or we cannot visualize more than 4 dimensions. Okay, so in the end, what we can do is to compare the distribution of data or how our data looks like with different pairs of combinations of principal components. Okay, in this case, on the left-hand side of the slide, we can compare how my data looks like when plotting PC1 versus PC2, and if we add a third principal component, a third dimension here, which can be principal component number 4, we can see that the distribution gains or gets the depth in this case, okay, from 2 dimensions to 3 dimensions, okay. So something that I would recommend you is to plot PC1 versus PC2, PC1 versus PC3. Always try to include the ones that contain the most information, for example, PC1 to PC5, more or less, and then create a different set of charts so that you see how the distribution looks like in the different projections, okay? Because usually you can find ways to classify data in this case, or ways to create regressions, okay? that are that you with which you will not need all of the rest of the principal components. Okay, so my advice is to always try to plot at least different combinations of up to five principal components in order to see this distribution. Okay. Also, what we can do is to plot all the original features when using the two first principal components. Okay, so if we have the first two principal components, okay, we can use this variables factor map, okay, in which what we are doing is, remember in the original chart that was like this, x and y, and then we have my data looking like this. Then we have this data looking like this, and with this data we could create principal component 1 and principal component 2, okay? We can do the inverse, okay? And instead of plotting my principal components on x and y, we can plot all my original features into the system created by PC1 and PC2, okay? If we do this, okay, we can see the relation or the how the information is combined across the original features. Okay, you can see here that we have a bunch of the original features across principal component 1, which is expected because it's the principal component that contains most of the information. Okay, and then we see some other original features that are closer to principal component 2, which is, well, again, uh, it's not weird because principal component number 2 is the second one that contains the most information. Okay, so this can give us an idea of how the original features are related to the new features. Okay, we can do, for example, the example of choosing a number of principal components using the cars dataset. Okay, and we can see here that by using three principal components, we are keeping, let's say, 93, 92% of the data. Okay, so if we remove the six worst principal components, we will only be discarding around 7% of the data. Okay, we will have reduced the size of our dataset to 1/3 of the original size, while only losing less than 1/10 of the original information. Okay, this is the main advantage of principal component analysis. So using the same example, using the cars dataset, okay, we can start plotting all my data points represented as black points, and the original features represented as these red vectors. Okay, we see that again across the principal component number 1, we have a bunch of features that are quite similar to it. Therefore, we could say that principal component number 1 is mostly a combination of MPG, SIL, DISP, and weight. Okay, and for PC2, we can say that it's a combination of gear, DRAT, I don't know what that is, number of carburetors, QSEC. Okay, we can really see here which principal component drags or gets more of the original features when combining them. Okay, if we increase the information in this chart a bit more, okay, we can see that we can plot all the cars, okay, that are represented by these original features: number of gears, miles per gallon, number of carburetors, horsepower, cylinders, displacement, okay. And we can see that there is a cluster of cars here. There is another cluster of cars here. There are some outliers or the cars that are different to the rest, let's say, okay. And if we kick it up a bit more, okay, we can see that these clusters are represented by three groups, okay, which are, in the red group we have the European cars, in the green group we have the Japanese cars, and in the blue group we have the US cars, okay. So this is why, for example, just by using PCA, we can create very basic, let's say, clusterization of my data without using more complex algorithm or complex methodologies. We can already create clusters according to how my data is represented on just two of the principal components. Okay, remember that originally in this case there were 1, 2, 3, 4, 5, 10, nine original features. Okay, but with just two, we can more or less see three clear clusters of cars. Okay, so that's the introduction to PCA. Okay, this plus the exercises that you did on the forum. I think this is a very good introduction to it. And if you have any questions, please text me or send me an email, and we can chat about it. Okay, thank you very much, everyone.